Okay, so for number 15, we want to notice that this equation that we're looking at here satisfies one of the conditions of one of the methods that we talked about for how to parameterize things. And so it's a sort of a generalization of the idea of a graph parameterization. Here, rather than, I mean, I guess you could interpret this as a graph in a way, but I'd rather just point out that we have solved for one of the variables in terms of the other variables. And when you have such a situation, then you can rewrite your position. Right, so this is, x. What we're trying to find is a function of two separate variables. You can just rewrite in terms of two parameters. I'm going to pick some new parameters. I'm going to call them u and v, like we usually do. So step one, the variables that you have not solved for, just let those be the parameters, u and v. Right? And then with those choices having been made, right, so y and z being u and v respectively, plug that into there, and that tells you what x needs to be. So x needs to be then, let's see here, y is u, z is v, so we get u cubed v minus u v cubed. Does that make sense? And notice this gives us what we wanted. This gives us position x as functions of two variables u and v. And so, wonderfully, even though, what this, whoops, wrong color. Even though, what this surface looks like, I don't know. It's a hard question what that surface looks like. No comment of what it looks like, but that parameterizes it. Yeah. Does that make sense?
Yeah.
Anybody else? Everybody happy?
So,
yeah.
In general, is parameterization just essentially the act of trying to represent some other thing in terms of another thing? In general.
Well, there's a lot of use of the word "thing" in that statement. Yeah. So fairly vague statement. But so the parameterization means we want to view a curve or a surface, in this case, as an image. Right? We want to find a function whose image is the object in question. And so, said differently, I want to find a function whose output values, or whose output points, the outputs from the function, I want them to cover the object in question. Here, I want to cover this, this surface with that equation there. Okay. Yep. And it just happens to be that, a great way to do that is this graph parameterization trick that we just talked about. Yeah.
Why do we use u and v and not stay with x, y, and z?
It's just kind of an aesthetic. It's a great question. It's kind of it's aesthetic preference on my part.
X, Y, and z as well, or
let me tell you what the problem is. The problem, as I see it, with doing that, would be that we would have so our parameterization is this function x, and note that would, as it stands, the inputs to this function are called u and v, and the outputs are called x, y, and z. Right? If we were to not do this trick, if I were to not, choose, let's let y equals u and z equals v, if I didn't do that whole thing, then what I would have is a function where the inputs were x and y, and the outputs are x and y and z. And it's just, it's uncomfortable that let's say x, for example, is both an input variable and an output variable. And it's not that you can't do that necessarily, but it's that it's just so much
so it would be
more
like
comfortable.
Changing the value of x, right? Through the
well, I mean, morally, this is the same thing because x equals, the formula for x is u. I'm sorry, I got these back. The formula for y is u, not x, it's y. Formula for y is u. But just by giving them different names, I just feel like I'm not confusing my variables. Confusion of variables is a dangerous little problem that try to avoid. And so it just it helps keep the hairs on the back of my neck from flaring up to do it like this. Yeah, yeah. But it's other people don't worry about it. Mm-hmm. Yep.
So
okay. Yeah.
Are u and v parameters?
Yep. U and v are the parameters. That's right. That's right. So the input variables are the parameters, and the function is the parameterization.
Okay, so kind of letting the y to be u and then z to be v because the equation gives x equals, so we kind of set the other values to be the parameter.
Well, I mean, so there's a trick that we use to get the parameterization. The trick is to make this choice that y equals u and z equals v.
Okay.
Yeah. Right. And that trick just gives me the convenience of avoiding the confusion of variables. Right. Yeah. Okay. Let me. Did you have it related to this or?
Yeah, I do. So
okay,
does x being a function have anything to do with x being equal to these two variables?
Well, x is not equal to these two variables. X is a function. The x vector is a function of these two variables. Does that make sense?
Okay. Yeah. So this x in the equation is a vector, or is that?
Yeah, so this, this x is just as a function whose components are x, y, and z.
So that x and that x are two different x's.
Yeah, the one with the little vector hat over it is that's a vector whose coordinates are x, y, and z. I mean, you got to give a name. This vector that has coordinates x, y, and z, you got to give it a name. Some books call it r. Okay. I find that confusing because isn't r polar coordinates? It's just, so I chose to call it x vector, and so you got to, notice, whenever that is there, then I'm talking about, the whole thing. And when it's not there, then that's just one variable. Right.